Today I'm going to be showing you the equations of motion through experiments. All we need is a stopwatch, an item to throw. I think we need something a little bit smaller than that. Much better. And a measuring tape as well. And somewhere to drop objects from. We can break motion down into some main quantities. The first one is displacement, written as the letter S. Now displacement means how far something has moved from its starting point, including direction. So if I move 3 meters to the right, my displacement is 3 meters to the right. But if I move 3 meters right and then 3 meters back again, I've travelled a total of 6 meters, but my displacement is 0. And that difference matters. The next term is initial velocity, written as the letter U. Now, this is how fast the object is moving at the start of the motion that we're going to study. For example, if I release a ball from rest, its initial velocity will be 0. But if I threw it downward, it already has some sort of initial velocity before gravity starts speeding it up even more. Then we have the final velocity, written as V. This is how fast the object is moving at the end of the motion we care about. So if we take a trolley and roll it down a ramp, its final velocity is the speed it has reached at the bottom. Then there is acceleration, written as the letter A. Acceleration is how quickly velocity changes in time. You might have already seen acceleration written as the change in velocity over time, or dv by dt. This could mean speeding up, slowing down, or even changing direction. A falling ball accelerates because gravity constantly changes its velocity. A car braking also accelerates, but in the opposite direction to its motion. So we often call that deceleration. Finally, we have time, written as the letter T, and time is how long the motion lasts. Now here we have 5 key quantities, and you might have already noticed they spell out SUVAT. Now SUVAT is just a way of describing motion using 5 quantities. S is displacement, U is initial velocity, V is final velocity, A is acceleration, and T is time. Now using these 5 quantities we can create equations of motion, but there is one key important condition. SUVAT equations only work when acceleration is constant. This means that they work really well for things like objects falling near Earth's surface, trolleys rolling down a smooth slope, or even vehicles accelerating steadily. But they do not work as simply if the acceleration is changing all the time, like a rocket launching, for example. So that's something to bear in mind as we make our way through this video. Now that we know what the letters mean, we can start using them. There are 5 key main SUVAT equations, and each one links 4 of the 5 quantities together. This means that you normally use a SUVAT equation when you know 3 values and you want to find a 4th. Let's break them down one by one. The first equation is V equals U plus AT. This one connects final velocity, initial velocity, acceleration, and time. So if something starts at one speed and accelerates for a certain amount of time, this equation tells us how fast it ends up moving. For example, if I release a ball from rest, then its initial velocity will be 0, but as it falls, gravity accelerates it downward. So after 1 second, we can predict its velocity. But sometimes we don't really care about the final velocity. Sometimes we want to know how far the object has travelled. And that's where the second equation comes in. S equals ut plus a half at squared. This tells us displacement when we know the initial velocity, acceleration, and time. So if I roll a trolley down a ramp and time how long it moves for, this equation can predict how far down the ramp it should travel. But there is a problem with this. In real experiments, timing something by hand is not very accurate, so if I start or stop the stopwatch slightly late, the result might change. So that's just something to bear in mind if you plan on doing these experiments in real life. The third equation is V squared equals U squared plus 2 multiplied by A multiplied by S. This equation is useful because it doesn't include time. So if I know how far something has travelled and how much it's accelerated, I can work out its final velocity without using a stopwatch, which is actually really cool. This is especially useful for experiments where timing is difficult, but measuring distance is easy. Then the fourth equation is S equals a half, all multiplied by open bracket U plus V, close bracket, multiplied by T. This equation says displacement is the average velocity multiplied by time, and that kind of makes sense. If acceleration is constant, then velocity changes evenly from the starting velocity to the final velocity. So the average velocity is just halfway between them. And then the final equation is S equals Vt minus a half at squared. And this one is like the earlier displacement equation, but it uses final velocity instead of initial velocity. So instead of asking where does it end up if I start with velocity u, it asks where must it have started if it ends up with velocity v. But here's the key thing. Each equation is just a different way of describing the same motion. The skill isn't knowing the equation specifically, the skill is knowing which quantities we have, which ones we want, and which ones we don't need. So before every experiment, we're going to make a little checklist. We're going to ask, well, what is S, what is U, what is V, what is A, what is T? And then we will choose the equation that leaves out the one we don't know and we don't need. And our first test is going to be simple. If I drop an object from a known height, can SUVAT predict how long it takes to hit the ground? Okay, so if I'm dropping a ball from this balcony, then I need to measure the height. Okay, so whilst I was trying to measure this balcony, do we have I found out that the height of the base of the balcony was 264 centimetres or 2.64 metres. That is, our S value is 2.64 metres, and we'll be using this later. Now, acceleration due to gravity on Earth is about 9.8 metres per second because Earth's mass pulls objects towards its centre with a gravitational force. This means that ignoring air resistance, a falling object's speed increases about 9.8 metres per second every second. So this is great, we can use this for our acceleration. So acceleration A here equals 9.8 metres per second squared. The initial velocity will be u equals 0 metres per second because I'm not throwing it, I'm just letting go. So the values we know are S is 2.64 metres, u equals 0 metres per second, A equals 9.8 metres per second squared, and T we don't know. We want to find out how long it should take to hit the ground. If we look at our SUVAT equations, we can find one that uses these quantities, and we end up with this one here. S equals ut plus a half at squared. If we substitute in our values, we get 2.64 equals 0 multiplied by t, plus a half 9.8 multiplied by t squared. The 0t disappears because the object is starting from rest, so we end up with 2.64 equals 4.9 t squared. Now if we divide both sides by 4.9, we end up with t squared equals 2.64 divided by 4.9, and so we just take the square root of this to find out our t value. And this gives us approximately a t value of 0.73 seconds. So SUVAT has predicted that the equations should take about 0.73 seconds to hit the ground. Now let's test it. Okay, so we have this ball here. We know the height of the balcony right here. We know the acceleration due to gravity. We know that I'm going to start this from rest, so the initial velocity is going to be 0. And when I drop it, we'll be able to calculate the time that it took to hit the floor. So let's see if we can calculate it by watching this video back and seeing how long it took. Okay, here we go. And look at that, we get a value of 0.73 seconds if we time it using the video. Of course, there might be some air resistance at play here, which these equations don't fully take into account. That'll be coming in a later video, but the important point is these equations work. How awesome is that? The next step is to look at what happens when we throw a ball horizontally, so not just from rest. Well, it now has two displacements. It moves horizontally, which we call x, and it moves vertically, which we call y. And now we can think of the ball's position as position x, y. The ball's motion has been split into two directions, horizontally and vertically, and each direction gets its own SUVAT equation. The important thing is that these two directions behave differently. Horizontally, there is no acceleration, assuming air resistance is negligible, because gravity is only acting downwards, so the horizontal velocity stays constant. And as an aside, we can kind of see this because if you take acceleration, which is just the change in velocity over time, i.e. dv by dt, and if this equals 0, then when you integrate, you're just going to get a constant. And so the horizontal velocity stays constant. Now, vertically, gravity acts downwards, so the ball accelerates at 9.8 meters per second squared. So here's the path when I throw a ball horizontally from the top of the balcony. I'm going to calculate the time taken from when the ball is thrown to when it first hits the ground, again assuming that air resistance is negligible. So let's look at SUVAT, but only in the y direction. We know the height of the balcony, which is 2.64 meters, so S here is 2.64. We know initially it's thrown horizontally, so its initial velocity in the y direction is going to be u, because there is no velocity in the y direction. Now we don't know v, the final velocity. We do know the acceleration in the y direction is going to be 9.8 meters per second squared, and t is what we're going to look for. So we need one of the SUVAT equations that has s, u, a and t in. We can use the same one as before, s equals ut plus a half at squared. And if we plug in our values here, we get the same value as before, 0.73 seconds. So let's try it out. We should get the time equals 0.73 if we watch this experiment back. Okay, so for this next experiment, I'm going to be throwing the ball completely horizontally, which means there's only going to be velocity in the horizontal component, so the x component of the velocity, whereas the y component is going to be 0 because I'm throwing it purely horizontally. So if we look at SUVAT in the horizontal frame, then we know the distance, we know the height of this balcony, we know the vertical velocity is going to be 0, and we know the acceleration due to gravity. So with all of that, we can use SUVAT to calculate the time it takes for this ball, when I throw it, to hit the floor. So let's do that. And hopefully afterwards I'll be able to calculate this by watching the video back. I need to throw it purely horizontally, this is so hard. And we get exactly that. Now, I want to try something different. If I knew the horizontal distance from the balcony to where the ball landed, what could I calculate here? Now, I'm back up here again, but I really need to use the exact same video that I've just done there, replicate the exact same throw, which I'm pretty confident I'm not going to be able to do. But what I can do, now that I know the time that it took for that ball to hit the ground, I can rewatch that video again, and I can calculate the velocity using the x components of the SUVAT equations. We know s because we've just calculated how far in the x direction it landed. We know a equals 0 because there's no horizontal acceleration, only acceleration due to gravity, which is of course in the y direction. And we just calculated t. We'd get that u equals s divided by t. Now I measured the distance in the x direction was 1.95 meters, so this would just be 1.95 divided by time, which was 0.73, which gives us a value of 2.67 meters per second. No 6-7 jokes in the comments, please. Now, I threw this ball with the horizontal velocity of 2.67 meters per second, and I was able to calculate that using SUVAT equations. How beautiful is that? The next question is, what about if instead of throwing horizontally, I throw with some angle? When an object is thrown at an angle, its velocity can be split into two components. The horizontal component is u subscript x equals u cosine theta, and the vertical velocity component is u subscript y equals u sine theta. You just have to look at a simple Pythagorean triangle to understand this. Now, in my experiment, I'm going to measure s subscript y, which is the height of where I've thrown the ball from, which we already know is 2.64 meters. Then I'm going to measure s subscript x, which is the horizontal distance travelled, which I'm going to measure. Then I'm going to calculate t, which is the time of flight of this ball, which I can calculate by watching the video back. Now, I don't know the launch speed and I don't know the launch angle, but I can calculate them by finding the horizontal and vertical components separately. So let's do the horizontal direction first. We're going to wait to substitute these values in until the end. Because there's no horizontal acceleration, we can take SUVAT equation 4, which would simply become u subscript x equals s subscript x divided by t, which here is just going to be our distance in the x direction divided by t. And this will give me the horizontal component of the initial velocity. If we watch the throw that I do, we can calculate t by just timing the shot. And here we get 0.94 seconds. Now, I measured the distance off screen, which was 1.9 meters. Then we would have the u subscript x. So the initial velocity in the horizontal component would just be the distance in the x direction divided by time, which here is 1.9 divided by 0.94, which gives me a value of 2.02 meters per second. Now for the vertical direction. We know that s subscript y is the height in the y direction, which we already know is 2.64 meters. We know the acceleration, which is due to gravity. Again, a equals 9.8 meters per second squared, and we just measured the time, so t equals 0.94 seconds. Now we want to find the initial vertical velocity, so the best equation to use is this one. If we substitute in the vertical values and do a little bit of rearranging, we get this equation here. Just as a quick aside here, I noticed that I didn't actually explain this in the video, but the reason why we get negative velocity here is because we're taking the positive axis going downwards, and so if we're throwing up here, it's the opposite, so it's negative. So basically you can imagine any numbers below the balcony are positive values and any numbers above the balcony are negative values. That's why we get a negative upwards velocity here. Obviously, if we look at it in real life, the velocity is positive, not negative. It just depends on the frame that you're using. So we now have both velocity components in both the x direction and the y direction. And to calculate the launch speed, we just need to use Pythagoras here with this beautiful equation here. Now we can also find the launch angle, which might be a little bit easier to see on the video itself, and we can do so with this beautiful expression here. And if you watch this video back, you can kind of see the angle yourself. How amazing is that? Now, even though I can't directly measure how fast I threw the ball, I can work backwards by watching the video back or by making use of what quantities I can actually measure. And by measuring the height, the range, the time of flight, I can calculate the horizontal velocity, the vertical velocity, the launch speed, and the launch angle. And all of that is pretty neat stuff. Now, of course, all of this has neglected air resistance, which plays a pretty important part in trajectories. And for that video, make sure to subscribe. Thank you all for watching, and a big thank you to my members who help contribute towards this channel and make these videos possible. I'll see you all in the next one.